We're going to start by considering why the matrix 2 is so easy to understand compared to other matrices. So let's see what it does. Well, when you take the matrix 2 and you multiply by the vector 1, well, obviously you just get 2 times the vector 1. And let's see this down on the graph. Well, you take 1 and you stretch it out to 2. So all it does is it stretches out the number. We can also see how it acts on negative 2. Well, it takes negative 2 and it stretches out to negative 4. And this is actually true for any vector on the line. If you take any vector on the real line and you multiply it by the matrix 2, you get 2 times the vector. Such vectors V we call eigenvectors of this matrix 2. And this number 2, we refer to it as an eigenvalue for the matrix 2. Now in general, if you have any matrix T and you multiply it by some vector V and you get a number lambda times V, we have special names for that. That's what this video is about, is that V is called an eigenvector of this matrix T. And lambda is its corresponding eigenvalue for the matrix T. Now we're going to actually look at a 2x2 matrix and see what's going on. So the matrix we're going to look at is 4, 0, 0, 2, and we're going to look at how it transforms the vector 1, 1. So I'll show you me computing it out. And you see we end up getting 4, 2, which is not 1, 1 just scaled. If you see, it kind of gets rotated and stretched. So it's not like multiplication. But instead, if we look at how it acts on 1, 0, while computing it out, we get 4, 0, which is just 4 times the vector 1, 0, which is very nice. On this, all it does is it stretches the vector out. Now, there's another vector like this, 0, 1. When we compute out its image under this matrix, we get 2 times the original vector. So if you look down there, we see that this vector just gets stretched out. So how you should think about this matrix is in terms of its eigenvalues, which are 4 and 2, and in terms of its eigenvectors. And what I've done is I've replaced those vectors with whole lines, because the whole lines form the eigenvectors of this matrix. And if we look back at the image of 1, 1, well, the thing is you can decompose a vector into these eigenvectors. And now you just think about, oh, well, 1, 1 was really 1, 0 plus 0, 1. And now let's just see, how does the matrix act on individual eigenvectors? And that explains why it did this weird twisting and rotating thing from before. It's just a combination of scaling along these different axes. Okay, I want to show you another example of some eigenlines. So we'll look at this matrix acting on 1, 0, and I'll compute it out. And we get 1, 2, which is not an eigenvector. If you see, it kind of twists and stretches out. So that axis, the x-axis, does not have to be an eigenvector. But if we now feed in 1, 1 for the vector and compute it out again, you see we get 2 times the original vector. So this thing is an eigenvector, and all we do is we stretch along this axis. There's also another eigenvector, negative 1, 2. Computing this out, you get negative 1 times the original vector. So you see this one flips, which is still kind of like all you're doing is scaling along that axis. So it's like multiplication. So again, this matrix seems kind of crazy, but you should think of it as just a pair of numbers on these lines. So on one eigenline, it multiplies by negative 1, and on the other line, it multiplies by 2. Okay, so don't get too excited because you won't always have eigenvectors. If we look at this matrix, which is a rotation matrix, and we multiply it by 1, 0, what happens? Well, we get 0, 1, which is just rotating 90 degrees. And let's apply it again now to 0, 1. We rotate another 90 degrees to negative 1, 0. So if you think about it, there's no way this thing can have eigenvectors like what I'm speaking of, but it does have eigenvalues, but they're imaginary eigenvalues, okay? Now, before we get into the heart of the video, where I show you how to compute eigenvalues and eigenvectors, we need to briefly talk about the determinant of a matrix. So the idea is I'm going to give you some matrix, and we want to think about what the columns are actually saying about it. So this matrix 4, 1, 1, 2, let's act on it by the vector 1, 0. We're going to spit out 4, 1, and if you look down, we're going to map that vector to a new vector. Okay, now let's also look at the image of 0, 1. That gets mapped to 1, 2. Now, these happen also, if you look at these vectors, they correspond to the columns of the matrix. Now, the determinant, which we sometimes denote by this bracket, it's just going to be the area of the resulting parallelogram formed by these vectors. Now, the way you compute this is sort of like base times height, but it's like base times height minus the other height times base, because you don't really have a rectangle. In this case, it's 7, and there's a general formula for determinant of A, B, C, D. Again, we do with these square brackets, and it's just going to be AD minus BC. So what's actually the point of a determinant? We're going to see how it's going to help us in the case of eigenvalues and eigenvectors. So let's look at this matrix 2, 3, 0, 0, and let's compute its determinant. And we get 0. And let's also point something else out. If we act on it by the vector 0, 1, we end up getting a 0 vector. Similarly, if we take this matrix 2, 2, 3, 3, we compute the determinant, we get 0. And if we act on by the vector 1, negative 1, what we spit out is a 0 vector. And the lesson here, well, I haven't quite proved it, but it's more general principle, is that the determinant of a matrix T is 0 if and only if there's some non-zero vector such that T maps V to 0, which is exactly what you just saw in the top two cases. So now we want to build some intuition on how to compute eigenvalues. So we're going to look at the matrix from earlier, 4, 0, 0, 2. We're going to act on it by 0, 1, which we know is an eigenvector, and we spit out 2, 0, 1. Now, check it out. If we also had acted on it by the matrix 2, 0, 0, 2, we'd also get 2, 0, 1. And now I'm going to write the 2 I'm going to write it in a weird way. It's still 2, but I'm just going to keep it so that we know there's like the left 2 and the right 2. But let's subtract the matrices. Since their images are equal, they map 0, 1 to the same thing. When we subtract them, we must end up getting the 0 vector. Now, simplifying this thing maps 0, 1 to 0, 0. And the idea here is that, well, this thing's mapping a non-zero vector to 0, so the determinant must be 0. And if we compute it, well, of course, we get 0. Now, pretend that you didn't actually know what the eigenvalue 2 was, and instead we replace it with an unknown variable lambda. Well, determinant of this thing must be 0. So let's plug it in, compute the determinant, and say, what does this actually say about lambda? Computing this out, we get 4 minus lambda times 2 minus lambda is equal to 0. So the possibilities are lambda is equal to 2 or 4. But we know that these are the eigenvalues of this matrix. So using this observation, what we're going to do now is figure out how to compute eigenvalues. Okay, so we're looking for the eigenvalues lambda of some matrix, some general 2 by 2 matrix, which we'll denote by A, B, C, D. Well, just like before, they're going to be the roots of the determinant of this matrix. They're the unknown lambdas that solve this equation. So let's do an example. We'll find the eigenvalues of that matrix from earlier. 1, 2, 1, 0. We plug in, we compute determinant of this thing with the minus lambdas on the diagonal, compute that out, you get this equation. And simplifying this, we can write lambda squared minus lambda minus 2, factored into lambda minus 2, lambda plus 1, and we get lambda is equal to negative 1, 2, which are the eigenvalues from earlier. Now, once you have the eigenvalues, it's pretty easy to compute the eigenvectors, and we'll do that now. So let's find the eigenvectors of any matrix. First, you have to know the eigenvalues. Then you pretty much just take the definition of the eigenvector, Well, you assume it's some unknown v1, v2, you plug it in, and you better get lambda times that vector. And now you're just going to solve this for v1 and v2. It's that easy. And we'll do another example. We'll find the eigenvectors from that matrix earlier, the 1, 2, 1, 0 matrix. We know from the previous problem that the eigenvalues are -1 and 2. So we'll plug it in. Let's take the matrix, multiply it by some unknown v1, v2. We should get -1 v1, v2 if it's going to be an eigenvector. And computing this out, so now it's just some algebra. We get these equations between the vectors. And taking the bottom one, that's going to tell us that v2 must be equal to -2 v1. Now, you're not going to be able to find out what exactly v1 is, because remember, it's not one eigenvector, it's an entire eigenline. But we do know this relation between v1 and v2. So we can replace the eigenvector with v1 times 1, -2. v1 can now be anything as long as it's not 0. You know, there's an entire line of eigenvectors. Similarly, we'll find the eigenvector corresponding to the other eigenvalue. This time I'm going to call it W1, W2. We get similar relations. Let's use the bottom one again of 2W1 is equal to 2W2. We replace that and say, okay, that implies that W1 is equal to W2. And now we have an eigenline, which is 1, 1 times any number. So these things, you can plug in anything for W1 and V1, and these form eigenvectors of the matrix. Okay, that's where I'm going to end this video. I'm never going to use purple to write again, and I'm not going to make it this fast.